So the second machine we'll cover is a spot welder. This particular one is a homemade one, but they all look more or less the same. So first thing you have to do is when you weld sheet metal, you have to set the time. Usually there's a setting for time. Some machines have also a setting for pressure. The pressure setting you can ignore, set it for maximum and leave it there. But the time setting you have to carefully set based on the thickness of the metal. And the way you do the test is you take two pieces of metal, and what you do is you make a few welds at different times and then check which is the right one. Okay, so this is about 0.7 millimeter, or maybe gauge 22 sheet metal. So we'll start with a setting of 2 cycles. Okay, now this thing sparks, so you need goggles, or unless you have glasses, it's good enough. And this thing, if you set the wrong setting, will drip molten metal, so no sandals, because it will melt the piece. Very important. In general, in shop, no sandals. Okay, so we do a bunch of welds. First we start with the 2. Okay, so you do a set of test welds to determine the right current. Start with 2 cycles, then we go 3 cycles, 4 cycles. That should be enough. Okay, now you do a tear test, and the test is the metal has to tear without the weld opening, and then you know that you have the right setting. So now let's zoom in and we start doing the tear test. So the first weld, the 2 cycles, should be open. Even the first weld was good enough, actually. You can see what happened. Look at it. The metal tore out from the hole without opening the weld. So obviously 2 is the right number. One is too weak, for sure, but 2 is the right number. For this thickness, if you change material or thickness, you have another setting. So after a few days you already know. You just look at the metal, you already know, or you make a little chart here. And you need 2 charts, one for stainless, one for mild steel. This actually only welds well steel and stainless steel. You can't weld non-ferrous metals. Okay. You can weld exotics, tungsten, titanium, molybdenum, all kinds of exotics. As a rule, you can only weld well metals which don't conduct electricity well, because the way it welds is by passing a current, I squared R. If it doesn't conduct electricity well, it gets very hot. Okay? If it could weld copper well, the electrodes would weld to each other. So you need 2 charts, one for stainless and one for steel, and you also need extra places in the chart if you want to weld studs or nuts and so on. Now, something to notice on a spot welder is that you can make a temporary weld and a permanent weld, which is very convenient for prototyping. So if I set it for 1, so we found out 2 was enough, but if I set it for 1, it will make a very weak weld, which I can break off with my hands, which is very useful for prototyping. So if I want to position something, just even for a moment, I just weld it on 1. It's holding together, but I can twist it off and break it off. So it's a bit like a temporary glue versus permanent glue. If I weld it, this is thicker metal, so if I weld it on 2 on the thicker metal, I can still break it off. Okay, I can still break it off if I try hard, but if I weld on 3, it's permanent. So this is kind of the limit what I can shear off. If I weld on 3, it's permanent. So it's recommended that if you're not sure, you have some covers to adjust, hinges to adjust, you tack weld on a lower setting, you can easily twist off. Once you're happy, you go over the welds at a higher setting. Now, if you welded it on the right setting, permanent setting, and you have to open the weld, If it's a single weld, you can maybe twist it like this. If it's a multiple weld, there's no way to twist it. So don't even try to pry it off, because as this test shows, it will tear the metal. So the only way to open it is drill it out. So it makes a nice center mark for drilling. So you pick a drill the size of the spot, typically 3-4 millimeter, drill it out, and it separates. Don't try other ways, it doesn't work.
If you have a spot welder that has both adjustable current and time, do you want to be adjusting the current to get different welds?
Very good question, very good question. You always set it for the top current and always adjust the time, unless the lowest time setting is still too high, and then you lower the current. Because there is no advantage in adjustable current at all, because the faster the current, the less heat escapes sideways, so the less energy you need to do a weld. For example, a laser welder is super short times, and it has beautiful welds just because of that. So what you want is to minimize the time, so that you maximize the current and just play with the time. But sometimes for very thin stuff, one cycle is already too long, or 1 cycle, 2 cycles is too crude. You want 1.5 cycles, so you go 2 cycles with less current. But this has adjustable current. I built this 40 years ago. I never used it once. Okay. So good. So now this one, as I mentioned, is a 15 kVA unit, and that's about the minimum you want. You want a unit which is anywhere from 15 to 25 kVA. So 15 kVA will weld something like 3 millimeter to 3 millimeter, or if you're used to gauges, it will weld like a gauge 12 to gauge 12, or gauge 10 to gauge 10, and that's the limit. And for that you need like something in the order of 15 cycles, I think. And that's it. It wouldn't take any thicker stuff. So let's try that. That's about gauge 12 steel. Yeah, that looks like you wouldn't be able to peel it off. It's too thick steel, but yeah, that's a good weld. So that's about the limit of what it can do. In stainless, it will weld a little bit heavier, maybe gauge 10 to gauge 10, and maybe a little bit heavier. And if you had a 25 kVA unit, you can go 1 gauge thicker, but that's it. It's not designed to weld thick stuff. Luckily, exactly where this range ends is where it becomes very easy to weld with a TIG welder. Because TIG welder needs a lot of skill if you try to weld thin stuff, because you'll burn a hole. But once the material becomes that thick, it's very easy to weld it with a TIG welder, even if you're inexperienced. So luckily, exactly where this ends, TIG welding starts. So there is no problem. Now, what it welds very well is rods. So if you want to make something like this, which is made from wire, it's ideal, and you can weld a 1/2-inch rod to a 1/2-inch rod with this. So it's actually very efficient on rods. One reason for that, because when you weld 2 rods, you have a very small contact area, and because you have a very small contact area, you have very high current density. So, and the heat cannot escape in 2 directions, can only escape in 1 direction along the rod. So the welding is much more efficient. So even a 15 kVA unit will easily weld 3/8 rod, and then weld even 1/2-inch rod. For example, even on a low setting of 5, okay, so it's a 1/4-inch rod and a 3/16 rod. It will weld them very nicely together. Maybe that's a bit under welded, but if not, we can increase the setting. Let's see this. And the test is the same. You have to twist the rod, and the weld should not open, the rod should shear. Same test. Let's see that. This probably is under weld. Yeah, I can still twist this. But if I went a bit heavier on the current, if I went, say, to an 8, it will break the rod if I try to. Okay. What a spot welder is also very useful for is to weld captive hardware, things like hinges, nuts, studs, standoffs. Another type of stud which will explain things like latches, closures. There's a very wide range of spot weldable hardware you can buy. So let's demonstrate this. Okay, so you have to make yourself a set of hollow electrodes to accept the standard sizes of screws. This is all metric, so this is all set for metric. That's M4, fits in this. Now, you'll notice that all these standoffs have a little ball and a spring over the ball in order to hold the captive hardware so it doesn't fall out. When you hold it vertically, it doesn't fall out. Okay? So you put it, say, like this, and set it for the number 8. It's good enough. So if I needed here, if I needed a couple of studs for later on mounting assemblies, what you do is you have typically with a water jet cutter, you'll make a little mark either by etch command or drill a 1 millimeter hole, but sometimes just an etch command is enough, because these studs have a little pip at the end, a little point. So what you'll do is you just go and feel until you feel the point and it falls into place, and that's what makes it accurate. You feel it locked in place. Okay. Okay, so now you have a stud, and again, if you are not sure about the setting, you do the standard test. It has to break the studs without opening the weld. This one didn't. It opened the weld, so it had to go to a higher setting, maybe a 10. Okay, so if you don't have the special weld studs, you can use a standard round head screw. Either Allen or Slot or Phillips, any screw with a round head works almost as well as a stud, except now we know we need a bit more current. So give it 12. Okay. Put this in here. Okay. Okay. And so now you can see it's welded. Okay, and then we do a brake test. Yeah, you can see the stud broke off without the weld, and then you know the setting. As I said, eventually you build up a table, you stick it on the machine, and you don't have to do this test again. Okay, now if you want to put a thread in some part, you can buy those nuts which have 3 projections. They are called spot welding nuts. They are available in wide selection in Imperial and in also more limited selection in metric on the internet. And the way you work with them, they have a pilot shoulder. You cut a hole where the pilot fits in, and that gives you the accuracy, and then you spot weld. And you spot weld with between 2 flat electrodes. So you align it with the pilot. Typically it welds at a high setting because it has a large surface area. The bigger the contact area, the higher the setting. Okay, now you have a thread. Sometimes you have to go and clean these threads, running a tap through them, because the welding itself can eject some metal, like here, into the thread. Now, if you don't like those, or if you don't have those, you can always weld just a plain piece and then tap it, because usually sheet metal is too thin to hold a thread, but wherever you want threads, you just weld a plain piece. And of course, a water jet cut hole is there, so you don't have to drill it. You just have to take a washer, let's say a washer, weld it at the back of this, and then you have double thickness, then you can tap it. The other way to do it is there are these inserts which look like pop rivets, which are thread inserts. You just put the holes with the water jet and the special gun which puts in the inserts. Okay? But the simplest way is those, because they are low profile, they're easy to use. Now, another thing you use sometimes is threaded standoffs, and those are welded like studs. So this goes with, where is the right size for it? Yeah, this goes with this side. So this is a threaded standoff. It fits in the same holder which holds the studs. Like this. Okay, and now you have a standoff here. Now, another piece of very useful captive hardware is hinges. Let's go back to this for a moment. So these you buy in long strips, many widths available. So for example, McMaster car, buy them online. If you need a box or a cover, you just line up the hinge like this, close, so it has room to close, and setting, you weld on a normal setting, say a 4. Now you have a hinge. So if you take this, you take this, now you have a hinged cover. Okay? As I said, there are latches, there are all kinds of things. Something that's very, very useful to weld is balls. And the reason for that is sometimes you need things like kinematic mounts where 3 balls register. Sometimes you need bars with balls at the end. So actually it's a very useful thing to make couplings or adjustments. So all that you need to weld balls is make yourself an electrode which has a conical hole like this. Okay, and it depends, there is 2 other electrodes. One is just to weld balls to flats. Okay, now because balls are very cheap and very accurate, you can take advantage of them in all kinds of adjustments, like for example arms which have to move in all directions. So for example, if I wanted to make an adjustment where I have a rod which I can move in any direction and lock, the easiest way to do that adjustment is to weld a ball at the end of the rod, put a washer over it with 2 screws which clamps the ball down, and then I can lock it. Okay, so for this I need to weld a ball at the end of a rod, and for that I put the ball in a conical hole, and I have a special collet adapter to grip the rod. Okay, but you have to think carefully whether you'll be able to take it out after you weld it, so you have to make sure that there is enough space that you can take this out and slide the ball out down. So the ball has to be smaller than the hole here. Now other places you need something simpler, you just need a ball welded here so it can sit and be an omnidirectional pivot or a kinematic mount. So you just do this, and setting is a low setting normally because it's a small contact area. You just put this here, and now you have a ball coming out here, which is very convenient. Okay. Now the conical adapter does touch the ball in one ring, so but luckily it has so much contact area that although it melts the ball at the bottom, it doesn't make any mark on the ball. So even if you look very closely, if there is enough contact area between the copper and the ball, there will be no marking at all on the ball. Okay. Another thing that you run into spot welding is sometimes you don't want the welds to be visible. Let's say you want to make something which has to be very beautiful on the outside, or sometimes for other reasons, if you make a medical device, for cleanliness reasons, you don't want anything on the outside which can trap dirt. So there's many reasons why you may not want to see. So if you look at the textbooks, they say that the way to do it is to take one flat electrode and one regular electrode, but when you try it, you find out it doesn't work. Because although this is a completely flat electrode, what it does, the molten metal, when it solidifies, pulls in a bit, and when you try to sand it, there is still a mark, although in this case the mark was quite small, but it's in. Because it goes inwards, you have to sand the whole surface to get it off. So the way to get an invisible weld is to make a special electrode which actually has a very small dimple at the weld point, And the dimple is maybe a few millimeters in diameter and maybe 50 micron deep. And what it does, it pushes the metal out into the dimple just by the amount which shrinks back when it cools down. So you end up with a perfectly flat surface. Okay, you have to still sand it a little bit, but it wouldn't. You would only have, at the worst, you'll have to sand off the bump, but it's much less sanding than sanding the whole surface. Okay, so that's how to make invisible welds. Now, sometimes you are stuck and you have to weld something which doesn't want to weld. Like, for example, a lot of stuff in medical is done with nitinol, which is a wonderful material, but you can't braze it, you can't solder it, you can't weld it. Okay? So what you do is you usually trap it between two pieces of stainless steel, so the weld goes across the nitinol and the two layers of stainless and welds everything together. For example, this is a flexure hinge made of nitinol. Okay, these are the type of hinges that can go 90 degrees with zero wear and zero lubrication. They act like a real hinge. So to give it a wide range, you have to use nitinol, but the nitinol you cannot spot weld. So we'll talk more about this when we talk about flexures, but basically you weld through the stainless. So, for example, if I have to weld some strip of phosphor bronze or beryllium copper, which is a very useful material, but it doesn't weld because it's a non-ferrous material, I can always trap it between two layers of stainless. It's the same if I want to weld a nitinol wire, I can slide a stainless steel hypodermic tubing over it, and then it will weld through the nitinol. So here, typically if you want to do that, it's a good idea to bond the ends so you have a nice gradual radius. So you don't have an abrupt transition, because any abrupt transition will be very weak. So if you look here, okay, you bend it to avoid an abrupt transition, and you weld it between two pointed electrodes. Let's see. And setting is more or less like the same setting you would use, a bit higher than you would use if it was just a stainless. So you trap the part. Okay, and now it's welded, and if you try to pull it out, it's actually very strong. I mean, there's some strange alloy formed in between, but you don't care. It's all melted through and becomes one piece, and it's strong enough. You can again do a test for strength, and it's very strong. You can't rip it out. So okay, so the last thing we need to talk about is how to make electrodes, because as you can see, a lot of these jobs require custom electrodes. So you'll have to make yourself a set of electrodes besides the normal ones which come with a machine. Okay, so now all the electrodes are made of copper. You just buy yourself a copper bar, square or round, and just bend it. Copper is very easy to bend. Copper is a beautiful material because after you bend it, it becomes work hardened. So if it's hard to bend, you can anneal it, soften it, bend it, because it'll become hard anyway just by bending. But it's easy enough to bend like this. Now, the tips of the electrodes are not made of copper, although you can use copper. You can just leave the metal itself as a tip, the copper itself, but this tip will easily squeeze and wear because copper is a bit soft. So if you want long-lasting tips, you have to insert tips, and these are made from either copper tungsten alloy or copper chrome alloy. So the cheapest is copper chrome alloy. You buy a rod like this. You can get it from McMaster Car. It's cheap, and this will last you for 100 tips. Okay, and you just a good way to machine it, a bit taper. Make a taper hole, press it in. Okay, so to make the taper hole, you just take a dowel pin grind it, taper, freehand. It doesn't have to be accurate. Just put in a drill against the sander, make it taper. Grind it flat to half the diameter. That's called a D-bit, and that's a milling cutter basically. So that's how you make yourself milling cutters, and because that is hard enough to cut copper. Okay, and with this you drill the taper hole, and then you machine taper on the insert and press it in. It doesn't have to be accurate because the copper will flow. So you just squeeze hard, it will make it on shape. So that's how you put the tips in. Because in many jobs you have to make strange electrodes, and if you have the copper bar, you can make electrodes as you need them. For example, sometimes you have to get deep inside a box or a cavity, so you need an electrode like this, which goes, so any kind of strange reasons you may need special electrodes. This has a short neck, so this one has extender electrodes, which you probably don't need. Most welders have a long neck. The longer the neck, the less the current, because this increases the inductance, especially when you have a big sheet of ferromagnetic material. So since this was designed to run on minimum power, it has a short neck to minimize inductance. So that's the reason why it's designed, but you can always extend it. Okay, now other specialty electrodes, you basically just make as you go. There is you make some very thin electrodes to get into little places. You make all kinds of offset electrodes to get around some fold in the metal. So this you just make as you need them. Electrode to weld blades together like a benzo blade. Okay, that's very much as a welder which comes with a benzo. Just when the benzo blade, electrodes to weld things at a precise angle. So this is just a piece of copper, scrap copper cut at a precise angle. So when you weld a rod, say a stud, to a piece, it will come out exactly at the right angle. Obviously that's if you need a whole bunch of studs all pointing the right way, you just make one electrode. So basically you just make them and throw them away if you don't need them, or recycle them. And there's many little special electrodes, like to hold a little part. Okay, so, okay. Now in general, you don't have to, if you have a part you weld to and you don't want to mark it except for the weld, you just need to give it a much bigger contact area than the other tip. So if you weld a 3 millimeter square, let's say, or 10 millimeter square, if the contact area here is 30 millimeter square, this part will not get hot already. So if I wanted to weld a stud here without any marking, all that I need is like a V. Okay, the moment this area is much bigger, it will not heat up. Okay, so I think we covered everything you need to know about spot welding. Besides the goggles and the shoes, it's completely safe because this is only 2.5 volts. So as I said, if I hold my hands on the electrodes when it welds, I feel nothing. But there are 5,000 amps flowing here, so you have to be aware of it, because if you are holding some magnetic objects or metallic objects, they will be attracted, because 5,000 amps is a significant magnetic force. So, okay, another useful thing you can do with a spot welder is build watertight enclosures, and the way you do that, you spread a very thin bead of silicone, RTV silicone, just very thin like this, okay, and then you weld through it, because the pressure of the weld will displace the silicone, and you weld through it on quite a dense pitch. So you set it up on 4, and it'll smoke a bit, okay, but it doesn't matter. See, the current tells you that it's still welded, although you didn't see any spark. Okay, so when you do this, what it does, it displaces the RTV. You can see it coming out, and it makes a completely watertight weld. So if you have to build a gas tank or something like that, that's the easiest way to do it. Okay, one other thing a spot welder is good for is to salvage little pieces of material to put in the water jet. Because of the clamping area of the water jet, you can't cut all the way to the edge. So if you have a piece of material and you want to use all of it, and you can't cut all the way to the edge, you want to attach a little piece so you can hold it. So the way you do it, you can either, if the materials are very thin, you can just put one on top of the other and spot weld, because it's scrap anyway. But sometimes the material is thick and you don't want to step. So what you do is you butt them like this. You butt them flush, and you put a weld on the joint, and it will weld them horizontally. It will just melt them together. So what you do is you go like this. Oops, that was missed. So what you do is you put a weld just on the flush. It's not a very strong weld because it melts it horizontally instead of vertically, but it doesn't have a step. It's smooth, and that's all that you need to grip it in the water jet.